We've talked a lot about how to protect systems and industrial systems, what the processes are, and how to set them up correctly. But sometimes it's interesting to look at the other side, how these systems are attacked. Fortunately, there's a service for this. We're testing it as part of security analysis. And me and Aleksandr want to talk about it now, namely some examples, the most interesting vectors of attacks on objects, of course, in theory, but interesting in terms of the technology used by attackers and that we use when we model attackers and how they get access to critical objects. Aleksandr, you're up.
Thanks, Sergey. Hi, everyone. So, yeah, we're talking about security. In the end, we took the SCADA through an engineer's laptop, connected, showed we had administrative access, completed the mission, and showed where we could go next. Then this happened. They said, well, you were in the inside, everything's fine. If you came from outside, nothing would have happened, and we also have monitoring. I see I don't have a lot of time, so I'll speed things up. A short introduction slide. If we talk in general about pen testing, assessment, and everything that goes with it, that it's connected to, it's important not to forget about an integrated approach. Oftentimes our customers say they did an audit, conducted a pen test, and installed a bunch of information security tools to a part of their perimeter. Everything is great there. Everything's protected, and they're not interested in the rest because nobody can get through. We closed our technological network. There's no direct network access to it. Everything's super, everything's great. Why do we need external? Who cares? We don't need it. This is the wrong approach because you don't know where an intruder or how they can get in, for example, from the external perimeter, or as they said today, through social media, through phishing. Other customers say, well, we now have a SOC, they'll do everything, they monitor everything, they'll fight off any attack. In general, yes, but the important question is, when they beat it back, will they notice everything on time? Will they remove everything? Or the opposite, when they forget about the technology segment, they check the external, launch a phishing attack, check their employees. But as for the technological network, they don't want to touch it because it's complicated. And if pen testers come, they'll launch something, some weird in-map of their own, and everything will crash. So we don't touch it. Everything's fine as is. If we talk about some of our cases and some of our projects, of course, they are anonymized. They only have a piece of the puzzle, not the whole thing. We also see a lot of customers who say, technological networks are too hard, let's just do the internal, just go ahead and get the admin domain and we'll see how bad things really are. Sometimes we seriously have to convince customers, like, let's look deeper, let's see what's there, where we can go steal something, etc. Here's one of our cases. It was an internal pen test. We had access to a remote DMZ. They wanted us to come inside and show how we got from the DMZ somewhere deeper. They started talking, we started negotiating, we saw their pain points and showed how we work in general, including technological stories, how we solve things, how engineers work, and so on. Here's an example how you can use people, how to use the social factor. In the pen test, everything was simple. We got out of the DMZ and into the internal network, gained a foothold in the internal network, took the Active Directory. How and what to do with the technological network is unclear. It's not even clear where it is, where to go, why to go there, and what to do in general. But with a domain, we have a forest, we can download accounts, we can see what rights the accounts have, see where they can go. We started studying, we found a couple shared resources available to engineers. Using these resources, we found various documents, including all sorts of network diagrams and stuff like that. Then we moved on. We've got accounts, we've got a list of engineers who service some SCADA, some technological things. We can access their computers. So that's what we did. Here we had 2 IP addresses, engineers' laptops. Engineers are great. They write documentation for themselves, how to go where, what's located, where what's configured, as we've already heard, including default passwords. One of the engineers had a document with a list of all the systems, including IP addresses, accounts, passwords, and even a list of previous passwords. Like this one was changed in month 7, this one in month 8. Now this is the current one. As we went through the documentation, we found which systems are used, what components are used, study the documents available on the network for these hardware devices. We understood how to reach them and connect to them. Great. In the end, we took the SCADA through an engineer's laptop connected, showed we had administrative access, completed the mission and showed where we could go next. Then this happened. They said, well, you were in the inside, everything's fine. If you came from outside, nothing would have happened. And we also have monitoring. I see I don't have a lot of time, so I'll speed things up. A major customer who approved us as a contractor, great people. They now things need to be comprehensive and they say, we've got this contractor, go check them out. So we went to the contractor. The contractor didn't have the kind of cybersecurity budget like our main customer. They're small and service and develop small systems. So their security situation was worse. In the end, an outdated system, Confluence, with a bunch of documentation on various customers who they serve. We took accounts from Confluence, got a password to Outlook using the contractor's passport, found the connection config in an email, connected. Then what? A couple of weeks later, we asked the customer if they knew we were already inside, and they said no. And it turns out they didn't monitor connections from this external contractor. For them, it was all pretty much the same. There was a small problem when at some point they saw the connection was from another region, but we just bought a VPS for the right place and we were back again. And again, the human factor. Inside, we got the admin domain. Now with the domain, we could look at what, where, and how. In reality, they weren't really doing anything wrong. There's a domain for the main organization, for the office network. And there are subdomains related to, let's say, factories, but there are bridges between the domains, reused passwords. The admins don't want to use a new password each time, so they reuse passwords. So we got the other domains, other accounts, and access eventually to the factory networks. And the rest is history. We find data, extract data, the same with engineer computers. You can't get directly into the ICS. It's hard to get there from the network. What's the simplest thing a pen tester can do? Just go and poke engineers, get into their computers, and then work from their computers. On computers, there's a lot of documentation, like where and why things are. So that's the infrastructure part. I want to say thank you. If you're interested, we have our blog, Solar for Race. Sometimes there are similar cases there, including investigations. So thanks, and I'll pass the floor to Sergey, who will tell you about the process control systems and industrial systems. Sergey?
Thanks, Aleksandr. Right, thank you. I lost my clicker somewhere. Really, I think after Aleksandr's presentation, PCS engineers definitely won't get involved in corporate networks and will stick to their own isolated domain. But let's move on to industrial networks. What does testing usually look like during security analysis? A group of specialists comes, around 4 to 5 people, to the facility with their laptops, connect to the industrial network, collect some information, and on the way out give a report to the customer. The customer is obviously initially neutral, but when we're working, it's impossible not to mention that they're stressed because some group of people is at their facility and connecting to its systems on their network. But on the way out, the customer is always satisfied. Because we, one way or another, show all sorts of vectors, how intruders can go from the corporate network to the industrial network, how secure the industrial network is, and plus we all understand MIA just fixes in. The industrial network aren't enough, meaning it's very difficult to fix an industrial network vulnerability because it's all about processes. And setting up a process, even just updating software, is a whole problem with lots of nuances, especially in an industrial network. So in our report, we're not just talking about how to eliminate vulnerabilities, but about detection and response methods, how you can fight, some additional measures. We work with different clients with different levels of maturity. There are customers who have well-established processes and technologies. There are customers who are only just getting started and still have a lot to do in terms of processes. But the truth is that the more mature the customer, the larger their report, because we as attackers will naturally try to bypass all controls, all processes they have. So most likely we'll provide much more information rather than when we just have a flat network with vulnerabilities. One of the interesting examples in continuation of what Aleksandr said is when the path from the corporate network is isolated by a data diode. It was a real data diode, it worked as a data diode, it was in the middle of the optics between agents and only allowed one correct connection physically, so it was impossible to get around. But during our security analysis, in the context of pen testing, we collected information about the network, about objects, how they work, and found that some nodes have a different address. We started asking engineers what's going on, how it works. It turned out they had a separate switch where you press a button and the network reconfigures. This existed to overcome one of the problems of security, software updates and updates of antivirus databases and the like. So the network is reconfigured, and at this point, an intruder could potentially go from the corporate network to the industrial network through firewall rules. Okay, so we found a fast vulnerability in this server located on the corporate network side. We told the customer how to fix all this, and the customer fixed it. There are lots of other examples when we were already inside the industrial network and worked with all kinds of equipment, like a long forgotten, not forgotten, but implemented by the industrial subcontractor router with its own SIM card connected directly to the industrial network. We discovered it, entered through some vulnerability. It turned out this router had a white IP address on the internet, so you could use the same vulnerability online and gain direct access to the industrial network. There were other interesting models from attackers that we used, for example, with the warehouse part of production. So there's a data collection terminal there, usually Android devices that have their own operation limitations. They can be bypassed too, or you can try. Then unload some of your own specialized malicious software that the attackers will continue to use. For example, carry out some commands next shift. They'll serve as some initial vector of penetration. Speaking about the vulnerabilities we find in industry, about how we help customers work with them and demonstrate to customers how attackers are likely to act, we first start talking about threats. With a threat model, what's most critical for the customer? After gaining access here, we can control both technological processes. So we do a lot of research, lots of studies of all kinds of industrial accidents. We present these studies here at international conferences, and there are lots of vulnerabilities that need to be corrected to find what we work on. As for the comparison and usefulness of such security analysis using the example of compliance audit, note that security analysis is a cross-section of the state of inflation security. It's necessary because it allows for the discovery of things I was just talking about. Bypass diodes give the same thing, the introduction of some unknown device on the network, the same zero-day vulnerabilities that can be in the equipment. This section allows us to discover it. I don't want to say that compliance is useless. No, absolutely not. It's simply different tasks in essence. And even they need to go together. I mean, compliance is about processes, and if we're talking about the current state of security of a customer's facility, compliance helps strengthen it, establishing processes, implementing technology. That's what it's all about. But if we add an attacker here who attacks the facility, they probably don't care what standard you're at. They'll take the shortest path that will be least noticeable. We try to do the same thing. We trust in the attacker's actions. And of course, we can pay some attention to the standard, meaning to the technical vulnerabilities we find, which part of the standards our customers don't comply with. We can also give them this information. But the story is that the more we do this service, the more we understand that by modeling attacker actions, we essentially become an attacker for the people at the facility. Because the more active actions we take, the more customers get afraid. I mean, there's always fear. You're letting people in, even in a big company with a good reputation. But even with an approved methodology, people will connect their laptops and do something on the technological network, the most critical networks. That's exactly what I wanted to talk about, right? About the problems of this service, providing services in industrial networks. Because these fears are justified, you can keep quiet about them, or you can talk about them like we constantly do. The fears are understandable. Somebody came, now something can go wrong, break down, everything, production, the whole enterprise, all transport, everything will fail. But the truth is, firstly, we're talking about facilities with high functional safety. You really have to try hard to break something. Secondly, we're talking about professionals who conduct these tests. When we do testing, positive that when we do testing of facilities, we never do our checks in production on critical equipment. We'll always allocate some kind of test environment where we'll check certain vulnerabilities. But when we're looking for certain separate parts of uncovered processes, for example, with the internal industrial router, it had to be somehow discovered. So some actions will be carried out in the network. They'll be carried out after we've been around the entire enterprise, seen the main technological process, all the critical equipment, understood how to operate it, what commands it responds to normally, which can lead to failures. However, the main point is still that is something does, after all, break down during some active actions, then it will break, not during our own work, but somewhere else. These examples are what I wanted to talk about. One of our favorite examples, we were working somewhere in a different country, and during our scan of the backup server, it started to reboot. At this point, their team ran up and was waving their hands, shouting something in their language we didn't understand. We didn't understand anything. 5 minutes later, they turn to us in English and say, "Guys, we've been trying for 3 years to understand why this server is rebooting. At these random intervals, please help. Why is this happening?" They gave us a binary. We looked at it and reversed it. It turned out that the service had an endless loop where it processed SYN packets and waited for the correct consequences of these packets. So it took up some memory, and when there was none left, the server rebooted. I should say that we work a lot with self-written software, and we understand exactly how not to work with it, and when to work with it more aggressively in an isolated environment, when you have to be extremely careful with it in production. And another case that happened, we had a production plant. There was some industrial software that obviously they needed some proprietary industrial software. So we couldn't see it at all in production. We took it to the lab. Luckily, the customer had a laboratory. We look at it, and it's Delphi. It turned out that this software with a certain packet, with any packet to the TCP port, just stopped working. As we later found out, the library used in this program, Current, was launched in debug mode. So upon receipt of any packet, the agent thought, okay, it's debug mode, we'll stop all the tech part we were responsible for. Other examples involve networks. You don't need to forget we're working. There's a network environment, only services. One of the cases was when we got a configuration of a network device, the topology was a ring. We realized that this network device isn't processing correctly what comes to it. If an addressee isn't found, these packets aren't being discarded. In the end, with monitoring, we showed the customer what was really going on with constant, for example, scanning by packet link inside. This router starts loading its CPU and subsequently can come to the port. That part of the segment just drops off. Right, that's also important. Another example was when we worked somewhere overseas, and after arriving at the customer site, we realized that while we conducted our initial reconnaissance activities on the network to collect traffic with the simplest ASMP requests, we realized that something wasn't working as it should. We see our packets arrive and get lost, but why, we have no idea. It turned out that a contractor had been there for a year, but was only supposed to be there a month, trying to understand this complex architecture, but they couldn't. We tried to help them, they told us where to look, but this happens too. You need to understand that there are very complex networks, so when we see something's not working right, then we won't focus on these networks, or we'll only handle individual ones that work predictably so as not to be some kind of cause for anything else incomprehensible in the further development of the process. There are a lot of cases like that we can talk about. We've seen a lot of them. Luckily, we've always caught them in isolated environments. And during our long practice, no customers have ever been harmed. The process always stays stable. Nothing happens with production thanks to our secure methodology. As for what can go wrong, as I said, self-written software, incorrect configurations of all kinds of network equipment, incorrect host configurations. Sometimes old equipment has worked for a long time, and when you get to it, you see it's been on for 5 years without updates, stopping, nothing. We did tests once with a customer when the plant was stopped, and we said, look, if we scan now, there are some risks. And when we started collecting data from the equipment, it just rebooted. As for testing, it's completely fine, but if it was in production, then it would be critical. So in general, at some point, we may help find things so they happened in a controlled window, and not when the factory or industry is operating at full capacity. To sum it up, I still want to say that it's necessary to do according to the state of inflation reserves in the industrial network. It's necessary because an attacker who eventually breaks through will still go to this network just in terms of technical discoveries, how they understand how it works, the information system, something we generally do. Besides all this, you can find a lot to learn from this, such as the fact that in general, our process for a strong industrial environment is also useful for Security Operations Center to understand where and what catch incidents, where they catch us on the monitor, where they don't, and so on. And at the same time, you can't forget that we have a safe methodology we've been perfecting for years. Now, the basic principles are here on the slide, and the most important thing is that, as I already said, this is a controlled test on a controlled perimeter. All the most critical things, we understand how critical they can be for industrial equipment based on our extensive experience. If it's necessary, we can make it happen. We use engineering software, critical attacks in an isolated environment, and all this helps us provide services safely and with great benefits for the customer. And that's all. Thank you very much for your attention.